talk about quantum form mapping.
Okay, so thank you very much for the invitation, and I'm happy to be back here. So, right, so my talk is about a quantum Kirwan map and symplectic vortices, and it's partly joined with Chris Woodward from Rutgers University in New Brunswick. Now, there are a few articles which I wrote, and then also there's a joint article with Chris Woodward. So the first one here is my thesis. Now the second one is an article which it's some technical result which is used in order to make things rigorous. And it appeared in the Journal of Symplectic Geometry in 2009. And this one here is also a technical result. So it's used for defining the quantum Kirwan map, which I'm going to explain. And it's on the archive. And then finally there is a joint article with Chris Woodward, which is more conjectural than the rest. So this is about functoriality for Gromov-Witten variants, and it's not yet a real preprint. It's on the website of Chris Woodward. Now, so we're still working on this. Now, let me give you some short overview. So I will start by explaining the setup, and I will say what I mean by quantum Kirwan map. So there's a general notion of such maps, and then I will explain a certain construction which should give such a map. Now this construction uses symplectic vortices, so that's the second topic here. And finally, I will give you some, some reason why maybe this map is interesting. So there's some quantum version of abelianization, and it involves this quantum Kirwan map. So this you can forget for the moment. I will need it later. Now let me start with the setup. So since this is not a symplectic or just symplectic seminar, but a symplectic and differential geometry seminar, let me remind you what the symplectic manifold is. So everything I'm saying here is about symplectic manifolds. So a symplectic manifold is a manifold M together with a symplectic structure which is a closed and non-degenerate two-form on M. So it's closed, which means d omega is 0. And first of all, omega is a two-form on M, and it's non-degenerate. Now, what I'm really interested in are Hamiltonian Lie group actions. But okay, before I tell you about that, let me give you just the standard example. We can take R2n with the standard symplectic form omega naught, which is the sum I goes from 1 to n dxi wedge dyi, where the coordinates in R2n are labeled by x1, y1, and so on up to xn, yn. Okay. Now, what I'm really interested in is a Hamiltonian Lie group action. So that's the following. We fix a Lie group G. So my favorite example is S1. Okay, the circle. Now, we call an action of this group on M Hamiltonian if and only if there exists a moment map for the action. So by definition, this means that well, this is a map from M to the dual of the Lie algebra of G. Okay, smooth map. So by definition, it's equivariant. And it generates the infinitesimal action. So this means that d mu of x v contracted with psi equals omega of x psi of x v for every x in M, every vector at this point x, and every element of the Lie algebra. Right? So you take the differential of the map mu at the point x, you plug in v, you get an element of the tangent space to the dual of the Lie algebra, which you can identify canonically with the dual of the Lie algebra. And then you contract this element with psi, which is an element of the Lie algebra. You get a number, this is a number, and this is also a number. Right? Omega is a two-form, so you can plug in two vectors. Here I plug in v, and here I plug in the vector field generated by this infinitesimal element, or element of the Lie algebra psi, and I evaluate it at point x. So the right-hand side is also a number, and the two numbers should agree for every choice of x, v, and psi. So such a map, mu, is called a moment map if it satisfies those two properties. Here I should say that equivariance is with respect to the co-adjoint action of the Lie group G on G star, okay, which is induced by the adjoint action. Now, here's a concrete example. You take S1 acting on R2n, which I identify with Cn. So the identification goes like this. You have x1, y1, and so on, and you map it to x1 plus I, y1, and so on. So we have complex coordinates here. And the action is given by z acts on z1 up to zn by simultaneous multiplication in each vector. Okay? And this happens to be Hamiltonian, so here's a moment map. Mu of z1 up to zn is defined to be the sum. Now there's some normalizations going on, so I guess this is the right normalization. So you have the sum 1 minus the sum I from 1 to n zi norm squared. Okay? So I should also put an I here. So this lies in the Lie algebra of S1, which is the same as IR. So I identify S1 with a subset of the complex plane. Okay. So as soon as you have a Hamiltonian action like this, you can do the following construction. Namely, you can look at the symplectic quotient, at least if everything is nice. So here is what this is. So namely, it's so sometimes denoted like this. Oops. M mod mod G. By definition, it's mu inverse of 0 divided by G. Now, this, well, you can always write this down. G, the action of G restricts to an action on mu inverse of 0 on the level set. But, well, in general, this is just a topological space. And the topology might not even be nice. But if G acts freely on mu inverse of 0 and properly for example, if the group G is compact, then this action is automatically proper. Right? And in all examples which I consider, G is going to be compact. So then, this here has a canonical smooth or manifold structure, and a canonical symplectic form, which you could denote by omega bar. Okay, and I'm always assuming that G acts freely on mu inverse of 0 in this talk, and that the action is proper.
Zero is also regular.
Yes, that's a consequence. You don't have to assume it. It's a consequence of this acting freely. Okay. But it's not enough for 0 to be a regular value for the symplectic quotient to be a manifold in a canonical way. You will get an orbifold if, right, in general, if you have that, not a manifold. Now, here's, again, back to the example. If we take this action here with this particular moment map, by the way, moment maps are not unique, but almost. You might change them here, for example, by some constant times I. Now, in this particular example, let's write R2n mod S1 equals Cp n minus 1, right? And mu inverse of 0 happens to be the unit sphere in R2n. So if you take the quotient of this under the action of S1, then you get Cp n minus 1. And the symplectic form on the quotient happens to be the Fubini-Studi form. So in particular, if you look at n equals 2, then you get mu inverse of 0 is S3 inside R4. And the quotient is S2 with, well, 1/4 of the standard form when you look at S2 embedded in R3, right? So we get that this quotient R4 mod S1 equals Cp1, which is S2, but the form here is really not the one you have from R3, but 1/4 of it. Okay. Now, right. So my whole talk is about symplectic quotients. So what I want to do is to study them. I want to understand, well, maybe invariance in general, but more concretely, Gromov-Witten invariants. So I should probably remind you what the Gromov-Witten invariants are. So first of all, they're symplectic invariants. And let's write down what kind of. Now, before I do that, I should maybe say for motivational reasons that the symplectic quotient corresponds to the reduced space in physical terms. So in physics, the Hamiltonian action corresponds to symmetries of the system. And then, well, taking the symplectic quotient means getting rid of those extra degrees of freedom, right, reducing the amount of degrees of freedom. And, right. So
what do you approach with moment maps?
Okay, let me remember if it has another name than moment map. Okay. You know, if you have an S1 action or R action, then the whole moment map is the same thing as a Hamiltonian function. Right? That's what it's called in physics. Hamiltonian function. Except there is an I here. Let's forget about that I. So it really corresponds to well, a function which generates your symmetry. For example, if you take, well, if you take, see, I just wiped it out, right? But if you take what I wrote here without the I, this is really the harmonic oscillator with some negative sign and some extra 1 here. Right? It's the usual energy. Right? Yeah. Well,
physical meaning of moment
Yeah, I would say this is the physical meaning. It's the Hamiltonian function. It's the energy function for.
Action.
So, well, action in what sense? For the sorry. There's another meaning of action in physics. Okay, action of the Lie group. Yes, right.
Well, got to be some constant of the symmetry. So I'm just wondering.
Yeah, I mean, there's this general Noether's theorem, right, which tells you that the one thing it tells you in particular is that under the time evolution of your Hamiltonian, the Hamiltonian is preserved. The energy is preserved, right? So, yeah. Right. I don't know if there is any other interpretation of it, but I think that's the real interpretation. It's the energy function which gives you the symmetry. But these are just words in the end, right?
Well,
so
depending on which symmetry you're talking about, sometimes it's momentum or whatever, so some other.
Yeah.
Constant,
right. Of course, the word momentum. Sure. You're right. Right. Of course, it has it comes from moment, right? In the end, so it's
a bunch of generalized.
Yeah.
Energy.
Yeah. Right.
Stuff,
Right.
Okay,
right. Yeah. Right. Okay. Now. Okay, so let's talk about quantum cohomology and Bronfik invariance. So that's what I'm interested in. Okay. If you have a symplectic manifold X sigma, then you can, well, at least philosophically, well, you can always define what I just write down here. It's easy to write down. Namely, you can define the quantum cohomology of X sigma to be the cohomology of X tensored with the so-called Novikov ring. Now, let's not worry what this is. Okay, let's take coefficients in Z and then tensor over Z, and this is a certain ring. It depends on the symplectic structure sigma. So this is not really interesting, right? You can write this down, but now the interesting thing is that there is a product structure on the quantum cohomology, which is a deformation of the usual cup product. Now, what it does is it counts pseudo-holomorphic maps from S2 to X. Okay? So, to make sense out of this, you have to fix a so-called almost complex structure on X, which is an endomorphism of the tangent bundle of X, which squares to the identity. So J squared is, negative identity on X, on the tangent bundle of X. And you want this to be compatible with the symplectic form. So that's where the symplectic form enters. That's the only place where it enters into this product structure. And, okay, let's maybe not go into too many details, but here's a picture. So what you do is you take 3 marked points on your sphere S2. Let's identify it with CP1. So you could, for example, take 0, 1, infinity. Okay? CP1 is the same thing as C union infinity. Now, you count holomorphic maps which at these 3 points evaluate through, given cohomology classes. Okay, so this defines the 3-point Gromov-Witten invariants, and based on them you can write down a product structure on this quantum cohomology. Now I don't want to go into too many details. I just want to give you the rough idea. Okay. So this is something people in symplectic geometry have been studying for the last 25 years or so. Now, in particular, maybe I should give you one example. So this here is a ring, right? You have a product structure in it, and there is some addition still, the old addition. Now, here's an example, just to give you again some idea what this is. Namely, if you take the CPN with the standard Fubini-Studi form, then what you get is this ring is isomorphic to the following quotient of a polynomial ring into variables P and Q by the ideal, so I do P to the n plus 1 minus Q here. Look at the ideal generated by this. Okay. So there is one relation, if you want, which we didn't have before. See, if you look at, first of all, this is now, it has an extra variable Q, which you can think of as e to the homology of CP1. And so this corresponds to an element in here, right? This is an element in here. Actually, in some version of this, there are several versions of this ring here. Now, this P corresponds to, to a generator, positive generator of the second cohomology of CPN. And well, if you do usual cohomology, there is no Q, so you could set it to 0, right? And then you have Pn plus 1 equals 0 as a relation. And that's the usual relation you have in cohomology. Now, this is a deformation, right? Quantum cohomology is a deformation of the usual cohomology. And that's what it is for CPN. Now,
So what if you replace the CPN form by some other CPN form?
then it's going to be different in general. No, in general it's going to be different. It's a symplectic invariant. Quantum cohomology is a symplectic invariant.
Yeah, but in this case, how they change?
I have no idea.
It's the same if you change to other.
I would be very surprised,
Multiply by another.
but I don't know a counterexample.
No,
I-
in this case, not the general case.
Yeah, but you're right. Even if I mean, I actually think it's an open question how many symplectic forms there are in CP2. If there is, oh no, that's no, it's different sort of thing. Anyways, so
Well, let's not get to that very
Okay.
thing. I mean, just
but
within the known
April-
not the unknown, if there's any, I mean, like exotic ones, but
right.
just like, for example, if you multiply by a constant, then is that going to change?
Oh no, if you multiply by constant, then it's not. It's the same thing. Right. That follows immediately from whatever the actual definition in the end.
But
but-
maybe you need some way to identify them, right? Or, I'm just wondering.
Yeah. Right. So if you change the symplectic form by just a, so a positive real number, so you do a omega. Now, see, when you take a almost complex structure J, which, so I didn't say how it's related to omega. It has to be compatible with omega. See, I'm sorry, I don't have time to really go into all details here. Now, if you take this J which is compatible with omega here, it's also compatible with A times omega. So you can take the same J, so you're counting the same holomorphic maps as before. And that's why the quantum cohomology will not change if you just multiply your symplectic form by a constant number. You can actually take an isotopy of symplectic forms, and then it will also not change. Because this gives rise to, well, there is an isotopy of almost complex structures which are all compatible at each time. Oh, right. Yeah, okay. There's some identification going on here.
Yeah, that's what I mean. So.
Yes, but there's a canonical map between the two. Yes, that's right. Yeah. Now, sometimes this ring here is really, something very simple. There's not a unique choice for this ring. So depending on your right.
You mentioned this exponential. So maybe it's different by e to the c. So when you change by a c factor, you multiply q by e to the c.
You don't do anything. You take the same ring in this particular example. You take z of q, the polynomials in q. In this particular example, you might take something different, but under some conditions which are satisfied here, you can take polynomials in some variables. Okay. now, okay, so here is what I'm studying in this talk, or what I'm talking about. Namely, it's the following question. Namely, how can we relate the quantum cohomology of the symplectic quotient? Okay, you can also write m mod mod g to a quantity associated with well, the Hamiltonian action on M. Now, well, okay, there are chromophyte invariants, but there are also equivariant chromophyte invariants, and there's equivariant quantum cohomology. So here is what it is. Equivariant quantum cohomology. I would denote it this way. It actually depends on the choice of the moment map mu. So, as well, say a Z module, it's H star of M tensored with some equivariant version of the so-called Novikov ring. Okay, whatever that is. So there's nothing going on here, but now again there is a new product structure, say star G on this. Okay, and the way it's defined is by using equivariant chromophyte invariants. Now these equivariant chromophyte invariants count holomorphic maps or pseudo-holomorphic maps into, so from S2 to the fibers of the Borel construction. So you take your symplectic manifold, you multiply it with, you take the product with EG. So EG is a topological space on which G acts freely, continuously, and EG should be contractible.
So you are using H star of M or H star of G of it. You just need the equivalent.
Oh.
Fiber of what? Of what map?
Let's think for a second. Yeah, I mean H star G. Right. Yes, sure.
So
yeah,
fiber
thank you.
of what map?
So you have the Borel construction here, right? You do M cross contractible topological space on which G acts freely, and you divide this by G. So this is a topological space.
Fiber of what?
Now this is actually a bundle over EG over G, which is also called BG, the classifying space for G. Now, as an example, if you take G equals S1 and our standard action on R2N, then this happens to be the same thing as, well, then you can take EG or ES1, you can take to be S infinity, which is the direct limit of the spheres S1, S3, and so on. And then this BG, or BS1, is CP infinity, right, which is the direct limit of CP2, CP4, and so on. And this quotient, so this Borel construction is really the same thing as, well, it's homotopy equivalent to this CP infinity, because here you just multiply with some contractible factor. So there's nothing really going on. You can take R2N cross S infinity as your new EG if you want. So okay, in this concrete example, right, you can say more explicitly what this is. Now we should think of this here. of the Borel construction as a fiber bundle over the classifying space, with fiber the manifold M. Right?
So what is your normative frame for, say, S1?
It depends on the form omega. Maybe
S1.
it still depends on omega. You mean for this particular action here?
Let's see, simple group. I'm just wondering what's the difference between this one with your usual.
Yeah, I didn't write that. Maybe can we discuss this maybe afterwards? I didn't write down the old one. So, I mean, this is an extra factor you have to add in order to make sense out of the product. Okay, it keeps. This is an extra factor.
Consider a situation that M is a point. You have the trivial action of S
right.
on the point.
Right.
You would have a quantum cohomology of the trivial action. So
right.
you have then you probably recover your Novikov ring from there.
Yeah, that's
So
yeah. They get the cohomology of the classifying space tensored Novikov ring. So this is this is a formal thing. This is not like
so it's just the
interesting itself.
So maybe just
but
the
maybe,
cohomology of classified space. I mean, this Novikov ring basically.
No, this is an extra story, right? When you have the trivial action on a point, then this is already the cohomology of the classifying space, right? And then you tensor it with some extra thing, which is.
What do you mean by HG?
But right, okay. H star of the Borel construction, right? M cross EG divided by G. Okay. There are other versions of the same thing. There's a Cartan model and so on. They're all isomorphic. Okay. Now, okay. Let me maybe point out that this equivariant quantum of cohomology has been defined by Giventhal and Kim in the late 90s, and right, there is a more, they did it in some heuristic way, and there is a more rigorous definition of it by Lu, which is also in the late 90s. Now, so what I want to do is, it seems to me like a natural thing to try to relate equivariant quantum cohomology with the quantum cohomology of the quotient. And that's what I'm trying to explain this talk. So this gives rise to the notion of a quantum Kirwan map. So first I should really briefly say what the Kirwan map is. Okay. So let's write it here. It's a canonical map from the equivariant cohomology to the cohomology of the quotient, without quantum, just equivariant cohomology. Now, what you do is you look at the projection from mu of 0 times EG divided by G to M bar, which is mu inverse of 0 divided by G, right? So there's again, natural projection map. And this is a fiber bond with fiber EG. Now, since EG is contractible, by assumption there is a section of this S, which is of course not unique. Now, you compose this section with the map to the Borel construction, the inclusion like this. And this composition induces a map, which I would like to note by kappa G, from the equivariant cohomology of M to the cohomology of the quotient, the symplectic quotient. Okay, and that's the Kirwan map. So it's easy to write down. Now what Kirwan did is she proved that this is in fact surjective if you take rational coefficients. And that's like the big thing about it. So you can use it to find out the cohomology of symplectic quotients as soon as you know the kernel, right, of the map. Now, okay. Now what I want to do is I want to have a quantum version of this. Now, in order to make sense out of this, I need to assume a few things. Okay, maybe let me just write it down here, but I will not have time to say what it means. So I assume that M omega is weakly monotone. This is a symplectic notion. And equivariantly convex at infinity, and I assume that the symplectic quotient is also weakly monotone. Now, let me point out that if you have the S1 action on R2M as before, then both conditions are okay. Okay. So here's a conjecture. Namely, there exists 1 omega mu algebra homomorphism so let's call it phi. So it goes from the equivariant quantum cohomology of M to the quantum cohomology of the symplectic quotient of the form phi equals the Kirwan map, and then I tensor it with the identity. So this is on the Novikov ring, equivariant Novikov ring here, and here I take a sum over second homology classes, equivariant ones, and then I do sum map phi b, and I tensor it with e to the b. So I need to explain something. So first of all, such a map I call a quantum Kirwan map.
You need the subscript G in the definition QH star and something.
Well, it's got a mu, so maybe.
Oh yeah, that's what the mu stands for.
So
but thank you.
Using the subscript.
Okay, thank you. Thank you. Sorry.
Are they same thing?
Yes, same thing. It really depends on mu. At some point I decided I wanted to have the dependency explicit.
So these two Novikov ring, I mean, the Novikov ring of this equivariant
Yes.
and the Novikov ring of quotient is the same.
No, it's a good point. I wanted to suppress this point. So what you do is you actually take, see, you have choices when you take the Novikov ring. There's not a unique definition. Now what you actually do is you just take the same Novikov ring. So you take the equivariant Novikov ring here, and you take the equivariant Novikov ring here.
So there's isomorphism.
If you take different rings, you get formally something different. Okay? And maybe sometimes really you get more information if you take a different ring. Okay?
But you're taking
So,
isomorphism between these.
well, not all of those rings which you might take are isomorphic, right? So you really just insist that we have the same ring here as there.
Okay.
Okay? You just take coefficients in that ring.
Okay.
Okay.
So you reduce that one in some sense, right?
I would say I'd probably make it bigger, right?
Okay.
But we can discuss that maybe also later. Now, such a map which satisfies this property here, right? It should be a ring an algebra homomorphism with respect to this ring here, and then it should, and then, well, with respect, most of all, with respect to the equivariant cup product on the left-hand side, which I just, well, formally say explained there, and then here you have the usual quantum cup product, right? You take the equivariant quantum cup product here, and here the usual quantum cup product, which is also given by counting homomorphic maps. Now, right, and it should have this form. So that's what I would call a quantum deformation of the Kirwan map, because here you have the Kirwan map, and then you will tensor the identity, right? And the conjecture is such a thing exists under the assumptions which I wrote down. Now, once this exists, well, in good cases, it will hopefully be surjective, and then you'll be able, well, under some assumptions, to calculate the quantum cohomology of the quotient. That's the whole point of it. Now, here is how I would define this map. So this is my second part. So this is idea of proof of the conjecture. So we define phi, and let's denote what we define by Q kappa G by counting equivalence classes, gauge equivalence classes of symplectic vortices on the plane R2. So I should say what that is, a symplectic vortex. So what you do is you fix an invariant in a product. On the Lie algebra of G. And you also fix a G invariant and omega compatible almost complex structure on the symplectic manifold M. So such a structure exists if the Lie group is compact. So let's assume the Lie group is compact. And I also fix a surface. So this is a two-dimensional real manifold. And I fix an area form, which means a two form on it, which is non-degenerate everywhere. And I fix a complex structure on this surface, which is compatible with this form here. So maybe once and for all, I should say what compatibility means. It means if you plug in J as the second argument into omega, then this should be a Riemannian metric. That's what compatibility means. And that's what I require here as well. And then finally, I fix a principal G bundle over this surface. And I call it P. Now I can write down what the symplectic vortex is. So a symplectic vortex is a solution UA, a pair UA. So first of all, U is an equivariant map from P to M, and A is a connection one form on the principal bundle P so it's a solution of the following two equations. So the first one is del bar JA of U, which by definition is 1/2 dAU plus J dAU times little j equals 0. And then the second one says FA, the curvature of A, plus mu composed with U times the area form omega sigma equals 0. And I should put the little star G here for, I'm taking the dual in the Lie algebra at this point, because mu is a map to the dual of the Lie algebra. So I identify the dual with its with G via this invariant in the product. Now I won't have time to really explain in all detail what these objects all are, but this is a twist. I mean, it's a deformation of the usual differential of U, and this is the curvature of A, and right here we have the moment map again. Now these equations were introduced by Zilibak, Gaio, Salomon, and independently by Ignacy Mundet. And well, Gaio and Salomon actually used these equations to calculate symplectic quotients under certain conditions, including monotonicity and some more restrictions. Now, what I'm outlining here is an extension of their argument. So they already defined such a quantum Kirwan map under very restrictive conditions, and I have a conjecture here how to weaken conditions, and then you have to really take into account these solutions of these equations. So let me tell you how. So, before I do that, let me point out.
What did you say something about Witten's equation?
I don't know which Witten's equations they are. I'm sure Witten already wrote down these equations somewhere.
Did you say that?
No, I said Zilibak, Gaio, Salomon, and independently they were introduced by Ignacy Mundet. So that was around 1999. So Gaio in her thesis studied a certain adiabatic limit in these equations. Or maybe it actually was before that, I guess. Now, so let me just maybe say something about these equations. I mean, okay, you might wonder, how would these equations help, right? Now, if there is, so here is how. So if there is no if there was no curvature term here in the second equation, then what we get is the Cauchy-Riemann equations for a map from sigma to the symplectic quotient. So, I mean, this is an easy proposition to show that gauge equivalence classes of solutions of this equation and of this equation without the curvature term are in one-to-one correspondence to holomorphic maps to the symplectic quotient. Now, if you have on the other side, so that's the right-hand side of my conjecture, right? On the right-hand side, that was the quantum homology of the quotient. No, by no I mean erase it. Okay? Look at the different equation.
Oh, right, of course.
Okay? So the curvature might be very big, but we don't have it in the equation. Now, if on the other hand we have no term like this, so we don't have the second term, and we actually have sigma equals C, the complex plane, then these equations really correspond to holomorphic maps from S2 to M. Okay, and that's what we're looking at on the left-hand side, right? We have holomorphic maps to the fibers of the Borel construction, and okay, the fibers are M, the symplectic manifold. And then philosophically, we should somehow have this viewpoint that we're really looking at holomorphic maps to the fibers of the Borel construction. Now, so what you might want to do is you might want to introduce an extra parameter in front of this second term and let it go to 0 and then let it go to infinity and show that solutions of the equations, you know, are in bijection when you do the limits. And then you would get some map like this, right? Now, this doesn't really work. And the reason is exactly that you have bubbling of symplectic vortices on the plane. So now you somewhat turn around your point of view. So you say, okay, so let's count solutions of the symplectic vortex equations over the plane. And then this should in fact give rise to the looked for quantum deformation of the Kirwan map. Now let's see how we count them. So, okay, so we consider the plane, and we take the standard structure, symplectic structure in it, and we look at the standard complex structure. Now, well, okay. So maybe, yeah. Okay, I should write this down. So as a matter of fact, if we look at the equations here, and for this choice of sigma, then every finite energy, so there's a certain notion of energy which is the Young-Mills-Higgs energy, and it generalizes the Dirichlet energy. Vortex UA such that some technical condition is satisfied, namely the image of the map U, the closure of it should be compact. So every such solution of the equations naturally carries a class, a second homology class, equivariant second homology class. Okay. Now, what we do is we fix such a class. And we look at the set of all solutions of the equations there, such that the equivariant homology class of U is equal to B, and then we divide by the action of the gauge group. Okay, there's an action of the gauge group on these solutions. And as a matter of fact, there are natural evaluation maps on this set. So the first one is evaluation at some point Z. So we go from this space MB to the Breuer construction. And this is for every, you can do this for every point in the plane. And then also an evaluation map, there's an evaluation map and infinity. Now this second map goes to the symplectic quotient, M bar. So you should think of this as evaluation at infinity in the union of R2 with infinity. Okay. So these solutions of the equations have a certain behavior, asymptotic behavior at infinity. And that's what we use here. Now, using these two evaluation maps, you can write down a formula for this quantum Kirwan map. So heuristically, we define the following thing. We define Q kappa G B of some equivariant homology class H star G of M to be the integral over this, let's call it a manifold. So that's already a subtle point, right? You have to show there's a canonical structure of a manifold here. And then you pull back the first equivariant homology class by this evaluation map here. And you take the cup product with the pullback under the evaluation map at infinity. And then you do the Poincare dual here. So what you do is, so this should be an element of the, I want this to be an element of the homology of the quotient, right? So if we take coefficients in some field, say R, then this is the same thing as a homomorphism from the homology to R, right? So I have to say what happens when I plug in a homology class. So I put the homology class here, I take its Poincare dual, I pull back this other class here, I do the cup product, and I integrate, I get a number, right? And that's what I want to get on this left-hand side, okay? So here's, and then what you do is you define the Kirwan map, quantum Kirwan map applied to alpha to be the sum over all second homology classes, and then you write down these expressions, and you have this element. So here I should probably write tensor, and then you have this element of the equivariant Novikov ring. So you sum over all second homology classes. So here is a picture. You have a symplectic vortex on the plane R2. Now it extends at infinity as well in the quotient, right? In symplectic quotient, it extends at infinity. So it makes sense maybe to draw a raindrop like this. It's not going to be smooth. The extension here is not going to be smooth. So that's why I have something like this. And then I have evaluation at 0, say. So here is my second, here's my equivalent cohomology class. And I take, philosophically, I take a Poincare rule of it, and I look at a vortex which evaluates at 0 through this Poincare rule. And then on the other hand, I look at, I want to have that the vortex evaluates at infinity through some other Poincare rule of a cohomology class in the quotient. And I count those vortices, and they should also have a certain given equivariant homology class. So that's basically what this expression here means, if you want. So we have to plug in the beta bar here. Well, the Poincare rule of it. Now, the question is, why should this give rise to a ring homomorphism with respect to the equivariant cup product on the left-hand side and equivarient quantum cup product, and then just quantum cup product on the right-hand side. So here is why. So you look at vortices with 2 mark points in R2 and then 1 at infinity, and you plug in 2 equivariant cohomology classes like this and 1 usual cohomology class in the quotient, and then you let those 2 points, they're fixed, but you let them move away from each other. And then in the limit what you get is something which I would call a stable map of vortices on the plane. So you have 2 of them, and you have a holomorphic map in the symplectic quotient. So this lives in M mod mod G. And this still carries a marked point, namely the old one here. And it has to satisfy condition here at this marked point, and then at those 2 nodes, right? Nodal points. And then you have those evaluation conditions on each of the vortices, right? If they're split apart. So that's what happens when you move the 2 points apart. But then if you move them together, the picture looks like this. So you get a vortex on the plane, and then you have a holomorphic map to a fiber of the Borel construction. That's what this is. And this holomorphic map still has 2 evaluation conditions, namely all the ones you get from here. And here's a condition on the vortex at infinity. Now this picture, if you can also go back from here to there. So this going from here to there is a bubbling argument, and going back is some implicit function argument. And gluing, so you need to glue a vortex like this with a holomorphic sphere like that, and here you need to glue 3 things. So then this picture says that the number of these equals the number of these, and this equals the number of these. And then, well, okay, this is only, you have to use some Bordism argument. Yeah, to use some Bordism argument, one-dimensional Bordism argument. And so in the end, what you get is the number of these configurations equals that. Now, what you see here, so here is the quantum cup product, the equivariant one, and then you have so you can somehow interpret what this picture means, right? You do the quantum cup product of alpha 1 and alpha 2, and then you plug it into the quantum Kirwan map. That's what I wrote here. That's what this side means. And this side here, on the other hand, means you first do the quantum Kirwan map, and then you plug this into the quantum cup product and the quotient, right? Counting numbers of these, and okay, then the picture says that the 2 agree. And I think my time is over. So let me just mention that. Okay, what I worked out is the bubbling argument like this, except that I looked at a case where there is where the symplectic manifold is aspherical, so then you don't really have bubbles here, but the statement is still interesting. So the equivariant quantum cohomology is just the usual cohomology tensored with the Novikov ring. There's no quantum going on if you have no spheres in M. And nevertheless, the statement is, the conjecture is still interesting. Now, so I did the bubbling argument, which says when you have a sequence of vortices like that with marked points, then and you have an upper limit on the energies, then there's a subsequence which converges to a configuration like this. And this is a more general picture here. And then also I proved the Fredholm result. So I defined certain Sobolev spaces of, weighted Sobolev spaces of pairs U and A on the plane. So the main feature here is that when you go to infinity, you have to think of how to weight your maps.
And you're talking about 2 things, right? One thing is non-sphere situation.
Yeah.
Are you still in that situation with something else?
Yeah, I'm still talking about no spheres, but when you go to the when you talk about the Fredholm theory, there is no difference. It's really about bubbling where the difference comes in. I mean, understanding spheres like that is actually not. It's not. It's not like it's something which has already been done. I mean, the real thing is going on at infinity. That's what you see here, right? When okay, maybe I cannot really go into details here as well, but so okay, there is a bubbling result. There is a Fredholm result. Yeah, Fredholm theory for solutions of the vortex equations over the plane.
Okay.
That's what, like the new feature. That's what you have to do. So it's about you have to find the right weights for the Sobolev spaces at infinity. There's not just one weight. I mean, you have to split your map into two parts and so on. Now, finally, well, what you still have to do, you have to do some transfer. Let me just maybe finish this.
Okay.
You have to do some transversality for solutions of the vortex equations over the plane to make sense out of an integral like this, right? I mean, so this should be canonically a manifold. For that, you need some transversality. And then finally, to prove that it's actually a ring homomorphism, you need, well, you need a gluing result. So you have to be able to go back from here to there and from there to here. And that's what well, still part of an ongoing project. And now I don't have time to mention the last part. So let me just say inverts. So the, well, one application of this map, once it's well defined, is that it gives rise to some quantum version of abelianization. So when you have, you take a maximal torus in your Lie group, and you look at the symplectic quotient with respect to that maximal torus. And you want to compare integration of cohomology classes over that quotient with integration of cohomology classes over the quotient where you take the full group G. So there is a formula by Martin which says how the two integrations are related. Sean Martin. Now, so Chris Woodard and I have a conjecture which is a quantum version of this formula. So in Martin's formula there is a Kirwan map.